Hello everyone, we're going to be looking at some free body diagrams today and how those actually work in physics. So we're going to go ahead and get started. I'm going to try to go as quickly as I can. I'm going to set a timer here real fast so that I make sure that I don't exceed, let's try not to exceed 15 minutes, okay? So the timer is started and let's go ahead and get going with these. So free body diagrams, what in the world is that? A free body diagram is basically just a diagram we use in physics to show the movement of an object and the forces that are acting on it. So let's look at some free body diagrams that we have here. So it says, for the free body diagram below, are the forces balanced or unbalanced? Well, let's look at this. This particular force here is a force up, right? It's going up. And what is the force of this? Well, it is at 20 newtons. So it's being pulled up with a force of 20 newtons. Well, what's going down here? We have another force that's pulling down. And it's pulling down at 25 newtons. So are these forces balanced or unbalanced? Well, clearly, I want to erase some of this so it's out of the way. Clearly, we have an unbalanced force. Okay, and so what is the net force on the object below? Well, to figure out the net force, you're going to have to take 25 one way, so it's going to be 25 this way, minus 20 this way, and that's going to end up being a net force of 5 newtons going down, okay? So you would say 5 newtons down. And that's what the box is doing. The box is actually moving in this direction. Okay, it's moving down. I guess not in that direction. That's kind of some kind of weird curve, right? It's moving this way, 5 newtons down. That's the overall net force. Okay, that's how we do these. So let's do another one. Ms. Elizabeth pushes a trash can, okay? So she's pushing a trash can and it moves across the cafeteria floor. Draw a free body diagram below. So this is going to be the trash can, okay? That's trash can. And she's going to be pushing it. And she's going to push it in this direction, okay? So I draw my arrow in that direction. And what's the force that she's going to use? And it moves across the cafeteria floor. Draw a free body diagram below. Label each force. Force of gravity. Oh, we got to put the force of gravity. The trash can is actually pushing down, right? So the trash can is pushing down with normal force, but it's also being pushed up with the same normal force, or with gravity force. So this is gravity. Gravity, no. Oh my gosh. That's normal force. My bad. So this is normal force right here. Normal force is pushing up. And gravity, if I can get it to right, maybe, come on, let's go. We'll do red. Gravity. There must be a dead zone right here. It's not, doesn't want to write. No, don't be like that. It's being a turd. Let's try again. I think my pencil came unpaired. Let me get it started back up here again. Come on now. There we go. So we have gravity. Come on. Let's try another color maybe. I don't know. Try again. Gravity. Gravity force is pulling down. And what about the force moving in this direction? It's going to be quite a bit shorter, isn't it? Now, when she's pushing it across this would be friction force. The trash can isn't going to like take off and slide, right? Instead, what it's going to do is it's going to resist that. As she's pushing in this direction, okay, she's going to have to apply a force, and that force is going to have to be bigger than the friction force if she wants it to actually move. So we'll say this is push force, the push force, and then this is friction force. So you could say in this case that gravity and normal force are balanced out because it's not flying up into the sky and it's not sinking down into the ground, but it is moving from side to side. So push force is greater than friction force. So that's something that you would want to know. And by the way, as I'm filling all these in, you need to fill yours in as well, okay? This is what you're going to be turning in later. So let's move on to the next problem. And I need to check something. I think somebody may have just logged in. No, they didn't. Okay, so then number 3, let's get that one. A free body diagram to show the forces acting below. So a plant is going to sit on a bookshelf. Draw the forces acting on the plant. Okay, so here we have our plant, and we can just kind of, here's our, it's going to have, a flower. Okay, there's the flower. And here's some more leaves. Okay, there's the plant. And it's sitting on a bookshelf. Okay, well, let's see. We have the force of gravity pulling this way. So we've got gravity. And what else? It's sitting on a shelf. So what else do we have? I'll go ahead and erase my plant so I can draw the next force in here. We also have the normal force going this way. Normal force. Now here's the thing. Is the plant flying up into the sky? No. Is it falling off the bookshelf? No. It is doing this. It is sitting still, isn't it? It sits. So are the forces balanced? Yes. If there's no movement, then all the forces are balanced. So I'm going to go ahead and write that down. All forces are balanced because it's not moving. It's not doing anything. Let's look at the next one, and I'll change my color here. This one says, you push a sled carrying your little brother across the snow. Okay, that's something we've probably been doing around here lately. We're going to be pushing this sled, and it's got your little brother in it. So let's see, this is going to be our push force. Is the sled moving? It says carrying your brother across the snow. Yeah, so it is moving. It's moving. So that means friction force is going to be smaller, right? So this would be friction. Friction force. And let's see, we also have what? We have gravity. We have gravity pulling down. And luckily, normal force going the other direction is going to keep it on the ground, but keep it from sinking into the ground, right? So there's normal force pushing up. And those are balanced. These forces are balanced because it's not sinking into the ground and it's not flying up into the sky. So gravity and normal are balanced. The only force that's really bigger than anything else is the push force, right? And we know it's bigger because it's actually pushing, it's moving the sled. So we could say push force is larger than friction force. Okay, so hopefully you're starting to kind of wrap your brain around how we're describing the object. And it doesn't matter what the object is, but we're describing the object's movement using physics, using vectors and forces. Okay, so let's try this next one. A person hangs from a bungee cord. Okay, well, we've got a gravity force, right, pulling down. So we have gravity. And then we also have the bungee cord. So this would be the bungee cord force is actually pulling up, even though it's kind of stretching, right, like a rubber band. There are no forces on side to side because it's just kind of hanging up and down, right? And it says the person hangs. So is this person moving? Is the person falling, or is the person getting sucked back up into the air like you would with a bungee cord? That kind of have that bow, bow kind of thing. It's not, is it? It's just that person's already done with all that part of jumping off on a bungee cord. So now it's just hanging there. So that means that the bungee force and the gravity force are going to be the same. So I could say bungee force, BF, is going to equal GF. because the person's not falling, but they're also not flying up into the sky. So BF equals GF. See, I just made it like a lot more lazy than having to print it out like this, okay? So I just said BF equals GF. Just trying to show you some lazy stuff. Okay, so now I'm gonna, I have to do one more down here at the bottom, but before I do, I have to erase what I just did with my fingers by accident. Okay, let's change color. Let's go with blue or purpley or whatever it is. So this one says, draw a free body diagram with 10 newtons of force and 25 newtons of force acting on an object in opposite directions. Okay, so I'm going to draw a box. There's the object. And we're going to have 10 newtons going in this direction. So I write it like this. I write an arrow with, I put 10 on it. And then on the other way, it's going to be in opposite directions. So I'm going to make this one longer because, you know, these vectors, they show magnitude and they show direction. So this one's going to say 25 newtons on this one, okay? So this side is pushing in at 25, this side's pushing in at 10. What's going to happen to this object? Describe the additional force needed to be applied to achieve equilibrium. How am I going to make sure that this thing doesn't move? Right now, it's moving in this direction with a force of 15 newtons, right? It's going in this direction with 15 newtons, but I don't want that to happen. So what if I took this guy and brought it around here and put it over here? In other words, I would, let me erase that off a little bit there. Maybe draw it out a little bit farther. If I bring that 15 newtons out and I put it in here, I could put another force right here, couldn't I? And that one would say 15 newtons. Is it balanced now? Yeah, it is. It's balanced now. Now I've got 25 newtons total on this side, and I have 25 on that side, so that's going to work out just fine. So I would draw it like that, and you can actually erase this guy down here. I was just kind of showing you how I'm trying to think that through, okay? So if you take a force of 10 newtons and a force of 15 newtons, that's going to add up to 25 newtons. So now, is this box going to move? No, the box is going to sit very still, and that means that we have a balanced force going on right there, and we have reached equilibrium, and equilibrium equals no movement. Okay, so equilibrium equals no movement, and that's what we want. How am I doing on time? Oh my gosh, I only have 2 minutes and 30 seconds left. Keep moving. Go quick. Hurry. So second page, this is the last page you're going to be doing. It says free body diagrams for 4 situations are shown below. For each situation, determine the net force. We want to determine the net force and acting upon the object and the direction of the force vector. So let's look at this first one. We have, and I want to just kind of poof it out here. We've got 3 newtons going up. Okay, so this is 3 newtons, and it's going up. And we have 3 newtons going down. Okay, so 3 newtons up, 3 newtons down. Is it going to be moving up or down? No, it's balanced. That's balanced. Let's look at this one. 5 newtons going in this direction and 5 newtons going in that direction. No, those are balanced too, aren't they? So in this situation, we're going to say 0 net force and 0 movement. Okay, so 0 net force, 0 movement. That's what's going on in this situation right here. Let's look at situation B. Let's go over here to this one. This one's got 3 newtons up, 3 newtons down. Is it going to be moving up and down? Nope, those are balanced. It has 5 newtons going in this direction, but I don't see any forces on this side, right? So you know what this thing's going to do? Which way is it going to go? It's going to move 5 newtons to the left, Okay, it's going to move 5 newtons to the left, so there it goes. All right, let's go down here to situation C. On situation C, we've got 20 newtons down and 20 newtons up. Is this thing going to move anywhere? Nope, this one's going to be balanced, so no net force. No net force, and it's going to say no movement. No movement whatsoever. My alarm's about to go off, so I want to go ahead and just pull it up here and just turn it off. Okay, pause. There we go. We've got a couple more. We're almost done. Might go a little bit longer than 15 minutes. I'm sorry. I tried. In this one, we've got 40 newtons up and we've got 25 newtons down. That's not balanced, is it? I'm going to have to figure out the net force. Net force is going to be 40 minus 25. What does that equal? That's going to be 35. That's 15, right? So this is going to be 15 newtons. So this thing is going to move 15 newtons of force. And which way? 15 newtons up, right? It's going to move up 15 newtons, or with a force of 15 newtons. Make sense? Okay, now let's do these down here. These are more complex. Free body diagrams for 4 situations are shown below. The net force is known for each situation. However, the magnitudes of a few are not known. So we need to figure out the magnitudes. Analyze each situation and determine the magnitude of the unknown forces. And write the unknown force next to it. Oh, we're going to have to fill in the blanks here. So we know that there's going to be 0 net force when it's all said and done. That means A has to be the opposite of this, right? So this one has to be 50 newtons. Okay, we have to have 50 on both sides. This is 200 newtons down here, which means this guy has to be 200 newtons up here because we have 0 net force when it's all said and done, right? Okay, so that works. Oh, look at this one. This one has a net force of 900 newtons up. Okay, well, we've got 200 newtons down. What does this one have to be up here? That's going to have to be 900 plus 200. So that's going to be 1100 newtons up. Okay? How did you get 11? Why is it 11? Why isn't it like 700? Well, because it says the net force. Okay? So that's going to look like this. It would be, let's see, if we have 900 here, that's going to be x minus 200, right? Oh my gosh, not algebra, Miss Bowman. No, not the algebra. And this is x. Okay, that's how that works. All right, let's look at the next one. The F net is going to be 60 newtons to the left. Okay, so that's going to be in this direction right here. That's going to be 60 newtons. Okay, well, we've got, let's see, this has to be 300 newtons, right, down, because it's not going down, it's going to the left. So this is 80, and that one is going to have to be what? Well, that one's going to have to be, again, we're going to have to do 60 newtons this way. I'll just erase that in, and I'll just put in 60 equals x minus 80. So what minus 80 equals 60? I'm going to have to get my calculator out. I'm not really sure. Maybe you guys already know the answer to that, but I'm going to double check it. So let's see, that's going to be 80 plus 60. That's how I'm going to find that. I take 80 plus 60 and I'm going to get 140. Okay, so this number right here is going to be 100, whoops, can't write it, 140 newtons, and that's going to be the answer on that side. Okay, let's do this last one. It says the F net is going to be 30 newtons to the right. Okay, so this one's going to go in this, no, it's going to go in this direction, right? Wait a minute, did I do that wrong? Did I do the other one wrong? I think I did. Look, you guys, it says to the left. That means it's going to go in this direction. I totally messed that up. Erase, 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 erase. Okay, so this has to be 60 newtons to the left. So you know what? I did that totally wrong. Let's erase this. We're going to end up with 60 newtons is going to be the answer. But that's going to be x minus 80, or 80 minus x. And that's going to be the other way around. It's going to be 20. Okay, so this is 20 newtons. Oh, I can't write it up there. Hold on. Hey, what's going on? This is 20 newtons. Okay, there we go. There's the answer to that one. Oh my goodness, totally messed that up. So this is supposed to be